All right, welcome everyone. And a lot of hands came up for the first time, but I want to kind of survey my audience real quick. Who here primarily uses technologies in the Linux ecosystem? Okay, and who here primarily uses technologies in the Windows or Microsoft ecosystem? Okay, I didn't expect as many Microsoft hands to go up. Spoken with this user group before, but all of what I'm going to show you today, the examples and the demos that I'm going to show you are around Azure and around .NET Software, Visual Studio. Now, Azure supports kind of anything that you can run in it, and there's so much for Mac and Linux that I'll touch on. But today is not specifically about the bits and bytes and the technology. It's about how to set up our teams for success. How many of you are responsible for supervising or leading a team? Okay. And the rest of you, how many of you are you work in a team under someone else's leadership? Okay. For all of you hands that went up, one of these days, the team is going to be yours. One of these days, you are going to be that team leader. And so tonight's topic is the things that we need to think about in order to run an effective software team of any kind. And since 2010 and up the last 8 years, the discussion around DevOps has really taken off. But before then, there was lots of discussion around the industry, around Agile and extreme programming and Scrum. I started my professional programming career with my first paid programming job, making $7 an hour in 1997, and I've been a programmer ever since. And although the roles you can call yourself, I've had all kinds of titles, but in my heart, I'm a programmer. That's what I am. Now, I could call myself the fancy word developer or software engineer, but I'm a programmer and it's fun, and I love doing this stuff. So we're going to dive in, and our agenda for today. Our agenda for today is, there we go. We're going to talk about the challenge that's before us as a software organization, some of the symptoms that we kind of see, a roadmap for how to put together a high-performing process and soup-to-nuts environment, and look at the details of how to put that together, and then show you some details about how the implementation looks in the Azure ecosystem. And just specifically, who here has never even done a sample or clicked over to Azure? Like, just not even looked at it. Okay, so most of you at least kind of looked at it and played around with it. It was somewhere in the mid 2000s when it first came out, and Azure came out with kind of a rough start because it came out with a platform as a service only play. It said, you know what? We're not even going to support VMs. We're going to have serverless only. And it had a way to run a website and a way to run an offline job, a service of some sort, and store your data. It didn't even have relational database. It was just blob and then kind of raw table. And that didn't get much traction because we weren't really talking about serverless 13, 14 years ago. We are now. So they had to backtrack and say, oh, people want VMs. Okay. I mean, they really begrudgingly, backtracked and said, okay, we'll offer virtual machines on demand. And now, of course, fast forward, we're all talking about serverless. Who wants to patch an operating system? Any hands? No, nobody likes patching operating systems. And so we're all looking forward to the day. So a little bit of contact information for me. I'm the chief architect at Clearmeasure, which is a DevOps-focused software engineering professional services firm. And a full half of our business is setting teams up for success. And so we see clients of all kinds and help them become high speed and high quality. And I'll talk a little bit about which one comes first a little bit later on, but feel free to write down my contact information. Yes, you can call my phone anytime. I'm happy to answer questions. Twitter, blog is up there. If you are on Twitter, One thing when I speak, if anybody fancies themselves a budding photographer, or if you happen to have a smartphone, snap a photo and tweet it to me. I appreciate it because I never have photos of myself speaking. That would be awesome. So, all right. Some organization, now, none in this room, of course, but some organizations still take weeks or months to be able to get out a next version, sometimes even to a test environment, much less production environment. And so the goal is to speed up that cycle, okay? Lean manufacturing and Kanban had conversations about cycle time and how much work was in process. And so DevOps kind of sits on the shoulders of extreme programming and Scrum and lean software engineering and Kanban, and then ropes in cloud and infrastructure as code all into this body of practices so that everything becomes programming. We're no longer managing the servers just independently as pets, as one analogy is, but everything becomes software driven. In a lot of cases, even the firewall rules and all of the network infrastructure becomes software driven. And so we want to move fast. We want to have a high cycle time. Some of the symptoms that we struggle with, and we think they're root causes, but a lot of times these are symptoms. Disruptive, long, error-prone deployments, if a deployment ever goes wrong. Delays. Have you ever had a stakeholder or someone up the management chain ask why it takes so long? And I've seen so many teams where management is looking at the team frustrated why something isn't done yet, why a release is not out. And they're frustrated with the team, and then the team, lo and behold, they've been working nights and weekends for a long time and busting their butts trying to get it out. And so there's a disconnect. Why do we have those delays? And then unmitigated risks. One of the common things that we see, and of course, this would never happen for anyone in this room, to get full data sets into pre-production environments and development environment, sometimes people take production data sets and then restore a backup to another environment or to their own workstation. And lo and behold, there's some data in that data set that is complete violation of any compliance or policies that the risk mitigators in the company think that they have in place. Because it's technically a little bit hard to build up sets of test data and hard to expunge it properly on a consistent basis. But there's root causes to these, and oftentimes a root cause will be an insufficient work environment. It's that there's either something missing from the physical or virtual environment, or a part of the process is missing, and that could be more of the root cause, but we're only seeing a symptom. Or it could be lack of visibility, lack of observability. We just don't see the work that has to be done. And I'll talk a little bit more about that. So there's a conventional view of how we put together a software process. And who's ever seen these kind of phases twisted into a sideways figure eight or the infinity symbol? Anybody? I see some heads nodding. So if you search for DevOps image or DevOps process on Google Images, you'll see this sideways figure eight. Lots of people are really adopting this view of DevOps as this sideways figure eight. All the while, the Phoenix Project and the Yellow Book, the DevOps Handbook, and even the new Accelerate book flat out are saying that's wrong. That's a different message. Now, not about the graphic, but the process where there's a process that dev does. And then over on the other side, there's a process that ops does. And then it comes back. So I just want to do an aside there because the whole DevOps conversation started about not having two departments or two things, but just making it the software team or the software department, and we have to do certain things. So I find it interesting that the common graphic is two separate things that just have pathways of communication or handoffs. So even probably developed by insiders. So this is the conventional view, and I just took that figure 8 and I untwisted it, all right? But this is the cycle we go through. This is the cycle: we plan, code, integrate, package, release, operate, learn, and then we take that learning into planning. Because Scrum will have you say that the product owner is all-knowing and that the product owner is going to prioritize something, and that's the right thing to do. In fact, when we prioritize something in the backlog, that's a hypothesis as to what will work in the marketplace. And we have to analyze it, figure some things out, make design choices, develop it, and then make sure it works right, get it up on a server and deploy it out to the users. And then the users are going to tell us, or we're going to learn from the people using it, whether it was a good thing to do or not. And there's research that shows about a third of the time we were right. And it was good, beneficial. About a third of the time we were wrong, and it actually made things worse. And about a third of the time it was just a change, and it really didn't make a difference, okay? So prioritizing something is a hypothesis, and that's a deficiency I think we as an industry have learned about the Scrum process and about that role of the product owner prioritizing things and deciding what's the right thing to do, because we're all guessing. And so that's why it's so important to iterate as fast as we can through this cycle and drive shorter and shorter cycle times, because only until we get a change out can we learn whether it was a good thing or whether we need to hurry up and back that thing off or turn the feature flag off or take it out somehow. I do have a hypothesis about how we got here as an organization that I think is instructional for how we actually implement the DevOps dream, which is to break down the walls and to not have two, but have one. Back in the early 50s, if you can remember that. Anybody? No. Back in the early 50s, if you ran some software, you were the one that programmed the software. And if you had access to the computer that could run the software, you were the only one that had access to that computer at the time. Operating systems just weren't a thing. And the few companies that did build operating systems were purpose-built operating systems, and they're more like an application framework that could just run their applications. I believe it was somewhere in the neighborhood of 1959 where IBM had their big infamous OS 360 operating system project that was a massive failure. They basically, IBM, at the time, as software goes, they were the Microsoft of the time. Massive company, and they gave that project an unlimited budget. Anyway, I digress. Fast forward, and we had mainframe operating systems where it finally became possible for multiple people to use a computer at the same time. And then we had remote terminals, all right? Now, who here has used remote terminals on mainframes? They were pretty fast, actually, weren't they? And so multiple people were able to use it at the same time, and then it became possible for one of the users to do something wrong that would deny service of the computer to the other user. They brought down the machine. Before that, you ran kind of one program at a time, and it wasn't multi-user. So the multi-terminal mainframe was the advent of the IT department, because there had to be somebody's job to protect the computer from that one user that would either on purpose or by mistake, most likely, take down the mainframe where it would crash and nobody else could use it. So at that point, now we had to have somebody whose job it was to protect the computer, to keep it running. Before then, that concept really didn't exist because you were the programmer, you were the operator, all right? And then, as the years wore by, different mainframes, mini computers, and then the modern server of today, but it all started then, and now we have so many people's jobs that exist, and a lot of people in this room, your entire career has been keeping it running because other people are going to change something that might bring it down. Okay, I see a lot of heads nodding because that's just the way it is. Now that created big IT departments because we had to keep things running, and so now our DevOps movement is about dealing with the organizational fallout that started with mainframe terminals and figuring out how to get those two sides of the industry back together. And some organizations have showed us how but it comes down to, if you make it, you run it. And if you're running it, you are also the ones to change it. Now, since my whole career has been on the Microsoft ecosystem, that's what I've gone deep in from 1997 all the way here. Now, I actually started on Visual Basic and some active server pages and JavaScript, well, that version of JavaScript in the 90s, and then cut my teeth on semicolons with C and Java. And so it actually was pretty cool when C# came out, because I said, oh, this is Java, but I know more stuff about it. Now, I've learned more since then, but in today's day, we have this conventional view of the process, all right? And we're trying to drive a shorter cycle time. But in order to do that, we're trying to bring these two sides back together. And there's a lot that goes into it. So we're going to look at this and we're going to dissect it a bit. And then we're going to look at how it's actually implemented for software that needs to run on Azure. So this first bit is so that we can see the strategy. Because if you're responsible for getting results out of a team, there's a lot that you have to think about. And if you're not now, you're going to be at some point. And even if you're not officially responsible for leading your team, you can really help your team by having a good strategy. So this is what I call DevOps-centered software engineering. I could call it Onion DevOps architecture if I wanted to make up an awesome name. But there are layers in here. And the layers that I've defined in here are other things that you have to think about. And we'll go through them. But the center is that automated DevOps pipeline. Now, in the DevOps user group scene and online and conferences, there's a lot of talk about how to go through the process, structure the Git repository, branching, how do I do a private build? What layers of automated testing do I put in my private build? When I push to the code repository, do we use regular feature branching? Do we use Git flow? Do we make up a branching structure? How do I structure the CI build? How long should it be? What do I put in? Do I put static code analysis here or later? Do I have chain builds? Do I have a build per branch? Do I have one build configuration for every branch? How many environments should I have in my pipeline? When do I deploy the first time? What's the structure of the package that I package up application components that I can deploy? There's so many questions, and there's so much focus on the actual pipeline. And is it Jenkins? Is it TeamCity? Is it Azure DevOps Services? Is it Circle CI? What about deployments? Do we use Octopus Deploy? Do we just sling a whole heck of a lot of shell script? But there's so much focus on the pipeline. That is your factory floor, if I can give you an analogy. That's your factory floor. And let me give you this mental picture of a factory where the raw ingredients come in one side and then the finished product ships out the other end. If you think about it, ideas come in one side of our pipeline. The mental picture of a pipeline is kind of linear flow. It flows from one direction to another. There's a start of the pipeline and stuff flows through the pipeline and it goes out the other end. And the ideas come in, and out the other end we need working software. And then we do it again, so it's a cycle. So the layers that we have to think about on top of just having essentially our factory floor where we can have workstations are the best practices that our team has chosen, our techniques for defect removal, what the workflow of the team is, our architectural blueprints so that we have agreement on what's being built, and cloud operations, how we actually run it. Because it's not just enough to build it, we're constantly operating it as well. And armed with that environment, then we can drive the cycle time lower and lower. Okay. So with each of these layers, and by the way, just send me an email and you can have a digital copy of these slides. Be happy to. Of these layers, each must have three things: a sound strategy, it has to be executed with discipline, and then have objective measures. It's not enough to say that you've equipped your team with defect removal, for example. But if your strategy is the selection of defect detection methods. Anybody ever heard of Capers-Jones, the researcher from? So he is probably the industry's most well-published researcher, certainly a leader in the industry, and he spells out a combination of defect detection methods that are proven to achieve the needed quality that we have. And so I'll touch on that a little bit later because defect removal is one of our layers. But let's touch on each of these. Okay, so best practices. Now nobody agrees on what the best practices are, but just think of the decision to choose practices. As a team, it's important that of all the possible practices out there, you actually choose what practices you're going to have. Maybe for longer projects, you choose release maps, or you use Kanban boards, or stable reusable components instead of custom developing everything. Do you use test automation, solid principles, onion architecture, continuous integration, refactoring, et cetera, observability? There's so many practices to choose from. There's books full of practices. But when you're putting a team together, if you don't strategically choose what practices everybody on the team is using, then each individual person is just going to pick their own practices. And if you don't have alignment and pulling in the same direction, then you're not going to go as fast as you could. So one example of best practices that is backed up by research is stable reusable components. That's the research term. Okay, stable. What does that mean? That means I'm going to use components that are already built. They're kind of certified, bug-free. They're really stable instead of custom developing something. Now, they've gotten really popular, and they're NPM packages or NuGet packages. There's all kinds of packages out there that do really cool stuff that we can just grab and use instead of custom developing it. But that's a strategic decision. And if you don't treat it strategically, then the software is just gonna be a magnet for packages, because people just bring them in and reference them ad hoc whenever they need something, and it's not controlled. And so treating it in a strategic fashion is actually having those conversations and talking about the architecture and choosing which packages and making sure that you trust the source. Everybody loves open source software, but nobody loves bad software or untrustworthy software or anonymous software written by somebody that nobody knows who in some country that, nobody, that is not a part of the global business community. So it's important that we know which packages we're using. All right. We find in our client work that when we inspect software in the development environment, oftentimes software leaders end up being surprised at what packages have been brought into the software, because we're just going fast and then those things are available. But it is a really good practice to do it instead of custom developing everything. All right, defect removal. Defect removal is the next layer. So if we don't think critically, oftentimes a beginning state for this would be that only code is evaluated after the fact. We build something and then we test it to make sure it operates properly, but we don't have defect removal at every other activity. We don't have a complete quality assurance mindset. We only have testing or finding the defects instead of preventing the defects. So we're not assuring quality, we're only finding gaps in quality. So research shows that far less than half of the defects are defects in the code itself. For every five defects, one of them is from problems with requirements. 1.23 is bad design decisions. 1.75 come from the code. 0.6 come from documents associated with the software, and 0.4 come from bad hot fixes. Okay, so when we think about finding defects, preventing it, just quality in general, out of every 5, only 1.75 are problems with code that was written. And that's from thousands and thousands of projects over the last couple decades. And there's an article. If anybody wants to read the article, you can Google it on your phone now. It's by Capers-Jones in 2012, and it's titled "Software Defect Origins and Removal Methods." All right. So some of the possible defect removal and defect prevention tactics that we could adopt would be exit criteria for every work stage. There's desk checking, which is, hey, does it run on my box? Pair programming, test-driven development, acceptance tests, pull requests, code reviews, static analysis, etc. And based on the type of software that we have, we need to strategically select the defect detection methods and the defect removal methods that are shown by the industry research to get us above 85% defect removal. I really implore you to read Capers-Jones's materials on this, because it helps us ground our team in where our quality is based on the nature of the software. How many defects am I likely to need to find? Because there are averages in the research. There are averages that, based on the technology that we're using, the type of software it is, and the number of lines of code, we can kind of do some math to back into what category we are in the research, so that we can guess at how many defects are likely in our software, so that we can know what percentage that we pulled out and fixed. All right. There are three, and I'm going to show you an example in the Azure ecosystem on this, but there are three defect removal techniques that are proven to get a team's quality up to 95% defect removal efficiency. DRE is the term for it. And those three are static analysis, inspections, and testing. Now, in the DevOps community, there's a lot of discussion about testing. And we all know that automated testing for a certain type of testing can be a lot faster than manual testing. And so there's different levels of test suites, which I'll talk about in a little bit. But inspections and static code analysis don't get as much play. Now, some people have started to adopt pull requests, which is good because that can fill the inspection role. And it's not just, hey, pull request, take a look at my code, but actually having a checklist for what it means to pass inspection. Has anybody ever hired a home or apartment inspector to come in and check it out? Yeah, so in that case, that's a professional inspector. You know what, I don't know about you, but I've been living in houses and apartments all my life. So I've got a lot of experience with that, but I still hire the inspector, right? And he's got a checklist, or she's got a checklist, and some are deficiencies. So with the pull request process, we can do the same thing quite easily. Just bullet point out, check this, check that, things like that. Now, static code analysis is one of those things where it helps to think strategically as well. Some of us probably have thrown in a command line for a JavaScript linter or some other static code analysis tool, but if we strategically think about that category, then we can look at all the different types of code that we have in our code base and make sure for .NET code that we have a .NET C# code analyzer. If we're using SQL, that we have static code analysis tool for SQL. And if we're using JavaScript, get some of those JavaScript linting tools. But that is where it runs every time in our build process. And between static code analysis, inspections, and testing, combining those three techniques, research shows that you reliably get your defect removal up to 95%. Now, in the extreme programming community, there was a lot of talk about pair programming. Does anybody use pair programming on a regular basis today? All right, awesome. That method has been proven to be very, very effective as well. But there's another thing that it accompanies with, that of all the quality assurance or all the things that impact defect removal in software application, it also tends to be one of the most expensive techniques. Really, really effective, but most expensive. So there, again, read Capers-Jones research. He goes through just painstaking detail about all of these techniques, how effective they are, and then how economic they are. And it's really interesting. But think strategically about it as a team. Bring up that conversation and really choose what defect removal and defect prevention methods you're going to apply. Okay, the next layer around the automated DevOps pipeline in our process and environment is team workflow. So most software project tracking tools use Swimlanes or statuses to move a piece of work through the process, but we find that the track status typically is at a much less granular level than what actually happens in real life. If the motion of the team is not reflected in the tool, then you'll have bottlenecks that happen, they remain hidden and sap the schedule. And your complete workflow, once you get it planned out, it really sheds light on every bottleneck source and enables the team to have a constant predictable flow. Let me give you an example. You probably use a tool that tracks work. In the Microsoft ecosystem, it's Azure boards, but Jira is also popular for some projects. Trello has gotten popular. There's anybody still using Rally? But there's all kinds of project tracking tools. Everybody in this room probably uses one. But how many of you would get into a pickle if you didn't open your email for a week because you didn't get something done? You didn't open your email for a week, and then someone says, "Why isn't that done?" Well, it wasn't on the backlog. I'm working off my backlog. Because probably every one of this also receives work via email, right? You have this awesome project tracking tool, and we're tracking work and we're tracking a backlog, but our email is like a secondary backlog, right? And so when we talk about team workflow, if we're really going to have a high-performing software organization, then we need to drive to a single source of work, making all the work visible, not have hidden queues of work. So if y'all remember that was a central concept in the Phoenix project. Anybody remember that from the white book? So it's really important to have every bit of work be visible and to know where it is. So who here, because I like it when you raise your hands, who here uses Swimlanes to visualize the work in your software team? All right, only 3 of you. Great. You're just tired of raising your hands. But if you visualize the Swimlanes, you know, Trello and some of the other tools, they start out in a very simple fashion of, oh, not started, in process, done, and it's up to you to make your own Swimlanes. The most effective project that I've seen in my entire career had probably 20 different Swimlanes. And I've come to really believe in so many implementations that none of the tools have a very good UI for representing the number of columns is really necessary to have every column have a swim lane. And so you're going to have horizontal scrolling. But if you leave it simplistic, like, hey, here's the backlog, it's not started, it's ready, I'm working on it, and then it's done, you're going to miss stuff. Remind me to get that screwed. So what we found is that even though organizations call it something different, the most effective project tracking methods really look at everything that's going to be done, who's doing it, and make sure that we have a formal status in the project tracking tool. For instance, yeah, there always needs to be an idea bucket, an icebox, a backlog. Just, hey, here's an idea. Let's not do anything yet. I just want to track an idea. Everybody tends to have something like that. But then there's a point where we say, okay, you know what? We're actually going to spend some time on this. We're actually going to start analyzing it and thinking about it. And there tends to be somebody responsible for defining what the heck the idea is. That's a column. Once we've defined that the details about it, you call it requirements analysis, for instance. Then somebody needs to make some types of design decisions about it. It's not even ready for a development team to write code. It's so far away from that. And it's not even ready to be estimated, okay? You can't estimate an idea. You have to make some level of design decisions, and typically it's not the same person that analyzed the requirements. Could be, but in a lot of organizations it's not. So now we're already up to 2 types of swim lanes. All right, so now we've made some design decisions. The next is for someone with a testing brain or a quality brain to come up with test scenarios. Okay, now that I know what this is, and we have some design decisions about it, is it going to run on the web? Is it going to run in a mobile handheld? Some design decisions, architectural decisions. Now come up with the test scenarios of how the heck am I going to test it once this is in place? Because if there's 3 pathways through it to test, that's a lot different from looking at it and seeing there's some variability and maybe there's 15 pathways to adequately test it. But all of that is necessary if developers are going to write the proper code. So what we find in a lot of clients is that the process is more anemic, where you have requirements analysis, and then the team is asked to estimate, and then it comes in, and now people who love to have their hands on keyboards and writing code are realizing, oh, we need to make a design decision. Okay, let's make this design decision real quick so we can get on to coding. And then they realize, oh, how many pathways, how would I test this? And then maybe they go back to the product owner and say, hey, when it does this, what do you expect this to happen? Because there's so much information missing, they're trying to have hands on keyboard and they're having to back up and fill in the missing piece of information. That in the factory sense, in the manufacturing sense, that's wasted motion. And when you think about it, it's really easy just to add another swim lane and say, we got to analyze the requirements, figure out what the heck it is, make whatever important, significant technical decisions that are necessary. We're going to figure out how we're going to test it once this thing is actually built. And then, you know what? Then it's ready for the development team. But we see wasted motion from developers going back and asking all these questions because the same type of stuff is omitted over and over and over again. And we don't have, what's also interesting is we miss a quality gate for requirements. Because remember, for every 5 defects, we have 1 where the source of that defect is requirements. Well, if we're going from requirements straight for, hey, team, estimate this and get it into your sprint, we don't actually have a quality control tactic to make sure that we catch the 20% of defects that stem from requirements. Whereas if we just put in that process of, hey, you know what, let's ask ourselves, do we need to make any key technology or technical design decisions about this thing? Does it introduce any new patterns? Does it introduce any new things where we need to adjust our architecture? And then ask, okay, once this thing is done, how would I test it? Doing those things is very profound, how it stresses the analysis that's done on the idea, and it actually finds gaps in the requirements. So things like that, analyzing your whole workflow, figuring out, hey, what do we typically do? And I haven't even gotten to the back half of the process. This is just the first half of the process that we've been trying to do for decades. And still now, you know, we're doing this cloud stuff, and it's awesome when we're spinning up servers and serverless techniques with the push of a button, and yet we haven't quite fixed waterfall yet in the small or in the big. So it's really important to figure out what the strategy is around the strategy element around your team's workflow, and make sure that you understand your whole team's workflow and have it properly represented in the tool. And now, this talk is all about Azure, but we haven't even gotten to anything Microsoft specific yet, because everyone, whether it's Jira or doesn't matter the tool, everybody tracks bits of work and it has some type of status, and you kind of order the statuses. So this applies everywhere. All right, now, this stuff was also kind of mentioned in the Phoenix project, because if you recall, work centers were discussed. And this is the same thing. Every swim lane in your process is a work center on the floor of a manufacturing plant from an imagery perspective. And you have inventory in front of the machine or the work center, which is raw materials that can be worked. And then you have output. And the goal is not to keep that station running full time. It's to have a flow from the entire station. But still, to this day, how many teams, and I won't name client names, but how many teams do we see where decisions are made because you have some number of developers and, oh, we need to keep our developers working, and developers code. So let's keep our developers working. So remember, all right, if you haven't read the Phoenix project, read the Phoenix project. It's an easy read, and the goal is not to keep any one particular machine, because remember Brent was always working, and he was the constraint, he was the rare resource. So let's maximize the usage of our rare resource, and then the whole thing was a bottleneck. So when we really spread it out and say, you know what, our business partners or our customer, whoever's paying the bill for this software team to exist, they have an idea. And from the moment they say, hey, I like this idea, let's go. The time from that to the time when they can use it in a working production environment, that is what we're optimizing, not any one of the swim lanes. So if we find that, hey, you know what, we had somebody, but we had somebody that was enumerating the test scenarios for how to test this once it's built, but hey, they're on vacation. There's no test scenarios. What should we do? Get a developer to do it. Developers are pretty smart. And so in the DevOps, there's some organizations that have really broke down the barriers, and actually there is one particular large team at Microsoft that published in video form and written form their DevOps journey, and they had test engineers and all kinds of developers, and they had sysadmins and support engineers and all this other stuff, and they merged an 800-person organization, and they have 2 job descriptions. They call it program manager and engineer, 2. And the program managers, that job is figure out what the market wants, maybe basically figure out what might be the right thing to do. And the engineer job is do it and run it. So this is one example, and 800, and they had silos all over the place, but there was one visionary vice president that was over that whole organization. And he said, you know what? No, we have 2 job types, program manager and engineer. Figure out what the market wants and what might work. That's the program manager. Engineer is get it done and get it online, get it working. And it forced everybody. It forced everybody to figure out to organize in a way that got the work done without resorting to discussing job title or whose job it is or who should do this or who should do that. Because when you're all, for the engineer, if you're all engineer and some test cases need to be written, or we need to analyze a big old spreadsheet of data, okay, who's going to take it? It's just a card. It's just a ticket of some work item. All right. So I spent a lot of time here, but if you're leading a team, it's so enabling to fully visualize what the complete workflow is. All right. You can also do some data analysis once you have a complete workflow. Let's say you have 10 different statuses, 10 different swim lanes. You can do some data analysis with start and finish dates, or when the cart, whether it be Jira or Azure boards. I can speak to those specifically because there's a really good API on both those products where you can get the history of every Jira issue. You can get the history of every Azure boards work item, and you can look at the timestamps of when it went from one status to the other. And if you just grab all the history, throw it into Excel, do a pivot table, it doesn't take much effort. You can do some business intelligence type queries and group by status, group by project, and you can actually see bottlenecks where you can say, wow, Jira issues or Azure boards work item, the ticket took 5 times as long to move from status 2 to 3 as it did to move from status 4 to 5. And then you can start asking yourself why and start to dig in. So use those APIs and start analyzing your data, because you want to find out your bottlenecks. If you have coarse-grained statuses of not started, in progress, done, you're never going to be able to derive analytics from your process. But if you get more granular and ask yourself, no, what are the real things that we do from having an idea to having somebody use it in a production environment, and then have a status for every one of those and sequence it out. And then now you've defined your workstations, and now you can say, okay, whose primary job do we want to assign to this? And it can be groups, just organize it however you need to. And so that you have work queues, and then move the work on through. And then using business intelligence, you can optimize the whole. All right, let's move on to architecture blueprints. Now, I like to say, if you can't draw it, you can't build it. Or if it can be built, it can be drawn, and if it can be drawn, it can be built. I don't know anyone who hasn't built a physical structure without some type of drawing. And so in the software world, in any world, it's the same. People who design things make some visual representation about what the thing is. I don't even care to talk about Visio or drawing tools. It could be a whiteboard, it could be a napkin. I have probably 30 of these black books at home. I do. Oh, look, I actually have an architecture drawing on this one. That's random. That wasn't planned, actually. But I draw all kinds of stuff. And what we find a lot is again, nobody in this room, that teams have no or out of date system diagrams or no blueprints. And there's some clients that come to us with an Azure environment where it started to sprawl. What happens, and this happens with AWS too, somebody in finance starts to notice the bill. Has that happened to anybody? Where it's got approved, the credit card's in there, and then, hey, wait a minute, why is this so high? And then they go through, well, just turn it all off. And you realize, no, we can't turn it off. Well, what can you turn off? I don't know. We've had, we come in and do this a lot where we sort out what happened because resources were spun up using just a web browser, right? Because now if you start from scratch properly, you're spinning up environments from script files that are stored in a Git repository, and you can recreate, and you're segmenting environments from an environment. But for teams that they first got into cloud, the first experience, hey, let's spin up something using my browser. And they're spinning up all kinds of stuff, and they're using the same account for a production environment as they did for trying something out. And so then they're like, well, I don't know let's turn that off. Oh, wait, production just went down. Turn it back on. Architectural blueprints of server environments is important, but also of the software that you're building. There is a model for software architecture that actually hails back to 1995, and it's called the 4+1 view, the 4+1 view model of software architecture by Philippe Kruchten. Has anybody heard of that? Okay, a few people have. Just look it up, and there's actually some YouTube interviews of the gentleman talking through it. And what that is a 5-piece view of how to put together essentially drawings for something in the software world. Now, the +1 is scenarios or architectural capabilities. And so in layman's terms, it would be the high-level bullet list of what the heck this system can do. Not every feature, but just the high capabilities. Does it show a product catalog? Does it allow you to add things to a shopping cart? Does it let you check out? Those would be bullet points of an e-commerce system capabilities. Because actually in the late 90s, there was a local business that wanted to get online, but in that day they didn't have the capability, nor did they have the desire to process transactions through the internet. This is a newfangled thing, but they wanted to put their product catalog on their web page and then allow somebody to put it in the shopping cart and get it over to them. So, and of course, and there it was an email order submission. So it was just the product catalog portion, and it was the choose my products and the quantity, and then hit the button with contact information. And then somebody at the store was manning that queue, would just call them up, and then they would figure out payment information. A lot of these are businesses, so it was invoicing or a check or using a credit card over the phone. So the +1 is the capabilities of the software system. Then there's the 4 layers. And the premise of the 4+1 model is that you have to have at least these 4 layers. In your environment, you may say there's another layer. But just like in civil architecture, we all know the floor plan view. We know the plumbing view. We know the electrical view. We know the HVAC mechanical view. And these are normal in building buildings. And you wouldn't think about hiring a builder without giving them a complete set of architectural plans with these views and a lot of times many other views. So the 4 views in the software world, the first one is physical, which now, yeah, we're all virtual, but in 1995, just the runtime view. How is this thing running? Is every bit of it running on a single server, or do we have a very wide web farm, for instance? Do we have any offline jobs? Do they all run together? Or do we have 20 different servers, each running an individual job? Do we have one database, or do we have a SQL Server farm? Do we have a single database schema, or do we have shards of data. It's just the runtime model. Okay, that's the one layer, because you can take one application and probably deploy it many different ways. And certainly we would deploy it differently in a VMware data center than we would in a serverless configuration on AWS or Azure. The next layer is logical. That is, if I look at the software as a developer, what are the logical, not even as a developer, but just even as the customer and the user, what are the logical pieces of the software? And it could be modules of the system that sometimes are available, sometimes not, or it could be layers or different components. So logical could represent the separation between the UI of an application, the core or the domain model, and then maybe a data access layer or an auditing component. And the arrows on such a diagram would be arrows of dependency. Which component, which logical component depends on the other. And the direction of those arrows are important, because who's ever worked on a system that was all one piece, spaghetti code? You couldn't separate any bit of it. All right, I know everybody's hand went up because you tried to blot out the painful memory. But you have the user interface, whether you remember the desktop software days or even on the web, you have a controller that it started out and it just called a query in the database, but then some business logic, some if statements, and now you have tons of code, and then you say, hey, you know what? This old application, we finally need to get it responsive. It's been such a long time. We finally need to move that to responsive web. So you start going through the code and realize, well, I got rid of all the code that was preventing us from going responsive, and there's nothing left, right? Everybody's had that kind of experience because there was no separation. If we were to draw the logical structure of that type of application, this is what it would look like. I'm done, right? There's no separation. Right? It's just all kind of one thing. So that's the logical. Now, in a lot of cases, there's a few architectural patterns, hexagonal architecture, onion architecture, clean architecture, that espouse something very specific when it comes to dependencies. And it actually, it's represented by concentric circles like this, where your core object model is in the middle, your domain model, your entities are in the middle, and then you have other layers around the outside that depend inward. And your data access would be one on the outside that depends inward. And that's a key architectural decision, to have business objects not directly call or depend on code that calls a data store, but to specify an interface of some sort and have the code that works on your data store implement the interface, and the dependency comes inward, thereby preserving the ability to change any aspect of how you store and retrieve data. And for systems that have been built like that have been on relational databases for a long time, and they say, you know what, let's go to a different type of data store. For this particular part, let's use a document store or a table, cloud table storage, because does this really all have to be relational data, or do I need something that's faster than the common relational engines? And so by doing this, you preserve the ability to change data access, and you don't have to change anything about business logic. But if you have your business logic deciding when and how to retrieve data for itself, well, now you're coupled. All right. Okay. So strategically, we are defining what we're building. And if we don't do this, oh, sorry, I got illogical. There's two more layers. One is the process layer, which is kind of like, you can represent it by a sequence diagram. For key transactions, what would be the order of things, the data flow through the components of the system? What happens first? What happens second? What happens third? What happens fourth? And then the fourth layer is development view. And I like to say that, hey, what's your DevOps environment? And because regardless of what you're building, there's a lot of concepts to describe in this layer. Source control, how's it structured? Branching, what is it? What are the steps of the private build script? Do we have continuous integration hooked up on this, or do we use nightly builds? What's in the continuous integration build? How many distinct environments are in our deployment pipeline? What are the activities that happen in each? What are the key technologies that have to be present in a development environment? There's all kinds of things to specify because the information's there, even if it's just tribal knowledge in your head. When someone joins the team, what do you tell them? You need this installed on your box and that and this and that, and you configure it this way, and you need to have your local database named instance called exactly this. And so many things that we tell someone who's onboarding on the team, but where is it represented, right? So that's the development layer, okay? So that's the 4+1. And we are aligning our team so that everybody can see the same mental picture. If you don't create an image of the system that's being built for your team, everybody on the team is going to construct their own image in their heads. And the likelihood is that everyone's image is not the same. So it's a really important alignment tool. And the 4+1 view model of software architecture is also set up as a iterative process. So even before extreme programming came out in 1999 and then the Agile Manifesto in 2001, that model expected architecture to be emergent and iterative and to be labeled and versioned and stored in the Git repository with the system that it describes. So that when you project forward and say, you know what, I think based on the stuff coming down the line, oh, and by the way, when do you decide if it needs to be augmented? Remember in that second swim lane that we were talking about after we analyzed the requirements and figured out what the heck we're going to do? The next step is make any key technology decisions. Based on this feature coming down the line, is it time to remodel our web farm or change the way we store data for that particular thing? Those are decisions. Either, you know what, the architecture is suitable for that new feature because it doesn't impact anything, or yes, this is a new thing. Let me pull up my architecture diagrams and let me decide how the architecture will shift in the development of this feature coming down the line. And then you check in the architecture diagrams into your Git source control right there. So if you want to go back in time, you got it. Okay, now the outer layer is cloud operations. Now, I could just call it operations, keep it running, run it. But going forward, everything is going to be cloud, meaning all of our infrastructure is going to be modifiable via code. That's kind of the big thing with cloud. Elasticity, infinite global elasticity is nice, and some cases are implementing it better than others, but that's still getting there. But the huge paradigm shift is we're not developing software so that it can run on an environment that somebody else has to procure and put in place for us, or somebody else has to give us, but we are essentially programming the runtime environment as we are programming the code that needs to run in the runtime. They're one and the same. That's cloud operation. So let's talk about incident management. If we rely on a user as the system is operating, if we rely on a user to report an issue, then we're only capturing a subset of the information that's available. We should see that a user was struggling, much less received an error, because we should know what's happening in the software. So that gets to logs, telemetry, observability. A lot of teams have some logs, but not enough. And in some cases, an admin, someone with administrative access, has to go into the environment, go into the production server to look through the logs, and there's not any aggregation. There's no performance timings. So the goal of this layer and making strategic decisions about it is to make the software completely observable, to know exactly what it's doing so that we can fix users' issues even before they finally get fed up and report them to us. So a lot of teams that we see have opaque logs and telemetry and are serviced by administrative user accounts, and they don't really know what's going on. And so some of the key methods that are available for selection are on the left there. Centralized logging, recorded telemetry, performance counters, automated log queries, threshold alarms. and non-admin incident management, meaning that incidents can be, and even alarms that are preventative alarms, can be worked by someone who does not have access to the production environment. Okay. So you see we have strategy, execution, and measurement. I'm going to show you an application. This will be brief, but here's two GitHub repositories that feel free to, they're public. One is the sample application, the sample environment that we're going to show, and it's being built up because I'm working on my next book, which will come out somewhere around April or May, and it's going to be, the working title we're going for now is .NET DevOps for Azure. It's basically how to do all this stuff in the Microsoft ecosystem. This will be my fourth book, and the working manuscript is in the second GitHub repository. I haven't really advertised it, but if y'all want to go and read stuff that hasn't been copy edited yet and has some grammar errors and whatnot, hey, feel free. There's 3.5 chapters in it so far out of 15. But anyway, feel free to write down those things and go to town. Okay, so let me show some of these examples. All right, so the pipeline. And by the way, I want to tailor. I want to go fast if this stuff is just old hat here. But who here? Let's see. Who here is on a team that has a private build script that everybody runs before pushing code to the Git repository? Okay, then I'll show it. So in 2006, from Addison Wesley, there was a book called Continuous Integration. That's kind of in 2009. A book called Continuous Delivery came out. But back in 2006, one of the first phase that was called the commit phase. There were a few steps in the commit phase of continuous integration. The first was the private build that just ran locally, and then in the commit stage was the server, the integration build that ran on the build server that was on the master branch. So the private build you could disconnect from Wi-Fi, take the laptop to the moon, and you should be able to run it, and it runs because it doesn't require any dependencies to run. So if you can see that, I'm going to run it. This is a .NET Core application on SQL Server, and it's just a PowerShell build script. Trust me that there's a lot of script here that you can't see. But essentially, it's going to decide and stamp a version number. Then it's going to do a compilation. Then it's going to provision the local data store, however we store data. Then it's going to run a unit test suite. And then it's going to run a component level integration test suite. Because in this form, we can't run all of our integration tests, but we can integrate our core of our application, business logic, with our data store because we have the data store running locally. Okay? All right, so it ran. And this is just PowerShell, by the way. Sometimes way back when we used NANT, which was a port of ANT. But now with PowerShell, there's a framework called Saki, but more and more, the tools and the command lines have gotten so simple, where now we just kind of script it together. And I'll show you what it looks like if I edit it here. Let's see if I can make the screen larger. And essentially, there's some properties at the top. There's initializing. We remove the directory so that there's no historical. Then we do a .NET restore, which is corollary with npm update. Then we do a compilation. Then we run unit tests. Then we run integration tests. And then there's also two helper functions, which are migrate the database local and migrate the database remote, because this is also leveraged in the integration build. And so our private build runs these PowerShell functions, and then the CI build runs the ones below. Try to do that. So anyway, that's a private build. And so anybody have a continuous integration build that takes longer than 3 minutes? Few people. Okay. The main advantage of the private build is it saves you a cycle of, oh, I missed something easy, and let me go to my integration build. I remember back in 2005, we were using cruisecontrol.net, and we had a build that we got to run in 45 seconds. The integration build ran in 45 seconds because we all the packages were cached, and there were some other things that were cached, and we got a 45-second. Now, today the tooling's kind of working against us, because if you run on a clean server, then I mean, how many megabytes is the npm packages folder? Anybody ever looked at that? NuGet's just as bad, by the way. I mean, 100 megabytes, 200 megabytes. Anybody ever measure? You going? So anyway, you want the integration build as fast as possible, but the reality is a lot of people are pushing the 10-minute threshold, which the 2006 continuous integration book says do not go past 10 minutes. Cut out processes, do as much integration as you can in 10 minutes or less, because a longer cycle, people just aren't going to do it, right? So the private build enables you to save a cycle if you just forget to check in a file or something stupid. And so you run that for yourself, and in a lot of cases on your own machine, it'll take 1 to 2 minutes to run, and then you check it in and whatnot. All right, so that's the private build. On the continuous integration build, this is what it looks like. Let me move this stuff over. All right, continuous integration build. Let's see, am I in the right spot? All right, that's a build that's already run. So let me go and show the, definition for it. Okay, this is a completely serverless build configuration. Now, notice the agent pool. There's always got to be a computer that runs it. This is using Azure DevOps Services, which is a platform as a service build server. I don't have to, click, 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 boom, it's up and running. It's hosted in Azure by Microsoft, and I can do build and deployments for Microsoft, Linux, and Mac OS. And it's 100% cloud, and it's kind of made to support any computer language. We happen to have the .NET application here, but it supports kind of any computer language and any operating system, including Mac. So and there's a lot of iOS applications being built here, because they've actually integrated Mac Mini racked Mac Mini capabilities for running this stuff. So it's kind of interesting. Anyway, so it's completely serverless. So the first step is we're creating a build database. And that is in Azure SQL, which I don't have to provision it. Again, this is 100% serverless. Create our database. We capture the connection string with the database that was created. I run the build script, which is build.ps1, which is the same script file that I just showed you. So most of my integration build is in source control. Now, same thing with TeamCity or Jenkins. You can have step after step after step after step after step, but most of that can just be wrapped up into a script file and put into your Git source control. And that way, integration build is less, that is unversioned, and you can make sense of it. A question? Mm-hmm. Yep. Yes, anything that you can run from DOS, PowerShell, or Bash, or anywhere. Because I mean, if you're on a Linux agent, you're running on Linux. Whatever script file you can run, if you're on a Windows server, if you're on Mac OS, any command line you can run. Just, yeah, anything you can put in a script file of any sort. That's right. If I were to go to project settings and go to agent pools, so this is the host that we're looking at. If I go to agent pools and look here, I can see all of the pools available to me, and I can look to say, okay, do I have anything running in the Mac OS agent pool? I happen to have, my account can run up to 10 of these agents in parallel. So, 10 Mac Minis running around doing my stuff. There's nothing in the queue. Let's see, VS 2017, the queue is on the right. I've ran a whole heck of a lot through that one. Okay. And then hosted Windows containers. If I'm doing Windows Docker containers, there's a Docker host agent right there that I can create images and sock them away. So that's kind of how it runs. For so many years, I was on TeamCity, And then a few years back, this product just, I mean, it zoomed past TeamCity, in my opinion. I mean, I've been in some of the JetBrains insider programs for years, and TeamCity was the build server that I swore by. But now, you know, we work with clients who have big TeamCity installations as well, and just a new client as well that has Jenkins. But this, I didn't used to use this, but as of 3 years ago, this is my #1 favorite build server. All right. Anyway, I'm not here to sell it. I'm just here to show it. So let's see. All right, the CI build, if I go back, that's what it looks like. The build script does the compilation, runs unit tests, integration tests, and then we have another task that's going to integrate the results of the test so that I can see the test. And then NuGet push actually takes the NuGet packages for my website, NuGet package for my database schema, which we're on SQL Server. And so if you're doing an integration build, think about that word, integration. We are integrating the various parts of our application and making sure that they work together. Because if they work together, then I can package up the parts into deployable containers of some sort, even if it's a zip file, and put them somewhere so that then I can deploy them to a downstream environment. Now, integration, I want to stress this. We see a whole lot of our clients coming and they have set up this product even, and they set up TeamCity or Jenkins, and they have the whole thing set up in deployments, but they're deploying their web applications, they're deploying their offline jobs, and then the database is 100% manual. The database is not part of the integration build. And that misses a whole point of continuous integration. So many databases, the majority of software applications out in the business world use some type of data store, whether it's relational or document or JSON or just a hierarchy of folder and file structures. They use some kind, and it has a schema. Even if you have a JSON store, you're going to have some type of schema. You're going to transform it. And a file directory, you're going to have names of directories. That's kind of your schema. You know, we obviously, relational databases have schemas. And so database DevOps is kind of something that people have been talking about, but that is a critical piece to continuous integration, is your database. And if it's missing, then you're not continuously integrating. You're compiling the compute part of your application, and you may be copying files of your compute part, but you're not integrating the application. And so if there's any of your applications, any of your teams that have one process for, just web applications are so common, your web application, and then a different process for how database changes are managed, then talk about how you can achieve continuous integration by bringing those together, okay? In order to fulfill the dream of DevOps, it assumes continuous or at least frequent integration. And so if you're missing that database component in your automation or your automated pipeline, get that taken care of. Okay, I'm going to jump forward. I'm going to skip past deployments and infrastructure as code because of time, but I want to show you the concept in the cloud operations of observability, and then we'll end there. So in cloud operations, we talked about log centralization, observability, and I actually have a build configuration that all it does is just throw a whole bunch of traffic at my website. So I'm gonna queue this up, and actually, this is just a script file, so I guess I could run it on a Mac OS agent, but oh well. All right, I'm gonna go to my logs here. And if I look at performance, so this is in the Azure portal. So you got AWS account that you can log into. This is the Azure portal. I'm in my Azure subscription, and this is part of, well, let me just navigate to it so if any of you are looking for it. So there's a whole bunch of resources here, but if you look for application insights, it's down in the DevOps section. Go to application insights, and it's going to show me a whole bunch of these. I'm going to pick the one that's for this particular example. And it's going to pop up some canned requests here. I'm not sure if my build has started running just yet. But I'm going to go then to analytics, because I know I have some traffic from the past. Actually, I will. All right, everybody get out your smartphones. CM Bootcamp Test Web. No, don't get out your smartphones. All right, I'm just going to look at the logs. I was going to play it by ear, but I shut down the web server before the talk, and so never mind. Okay. Oh, okay. Let me show you the examples. So this one, okay. This is the one that I'm prepping for the book. And if I go to the build, this is the non-optimized, hosted, serverless, and it took 4 minutes and 16 seconds. A minute and a half of that is getting packages and cloning the Git repository. So before the book goes to print, I'm going to show the optimizations of how to use your own agent, which then you get the Git cloning caching for free, and you get the package caching, and then every single one of your builds, you're saving a minute and a half of that. Because it's unreasonable for every single cycle to do a complete package Git, regardless of what packages you're using, and a complete fresh clone from Git. That's not what we do locally. We do a Git pull. We don't throw away our local working copy and just do clone constantly. We just do a Git pull, all right? All right, but let me show you the logs, because in Azure we can do log analytics and look at all the traces. If I just double tap that, I can see all of the traces for the particular application, and then I can use a BI type language to see, oh, look at that, crash dump initialization failed. That was the log from that exception that just popped up. And I can see, you can see it's sort of like a JSON type structure in there, but this is a NoSQL style database. And if I were to look at some of the canned where city equals, no, not city, where state, and it has some IntelliSense there. I want only the traces from Texas, meaning I had a server in Chicago in Azure just hitting my thing all the time, and I want to filter those out. So let me show only the things from Texas. I mean, you can filter till the cows come home, and then you can see that architecturally there's a trace message of, oh, an internal message was sent down the bus. Now this happens to be a log message. It's just a log message. Something happened, and that's how it's manifested. But it's wrapped. Every single log message is wrapped in so much other information so that it transforms, when you put it in Azure, it transforms a text log file where you're just looking at whatever you put in the text log to the log message that goes to this service in Azure, where every message is wrapped by all kinds of contextual information. What environment? Was it a log from DevOps, UAT, staging, test, production? What node on production? So that you can filter and actually have all of your telemetry active on your entire pipeline, not just production. Because how many times do we figure out there's a problem in production, and then we go and start looking at the logs that we do have and realize, oh, we don't have that information. Whereas remember all those key design decisions at the beginning of our process? One of those design decisions is, how are we going to make sure that our incident management process or our cloud operations process is going to properly support this new feature once it's actually done? And is our current telemetry method suitable for covering this, or do we need something else? That's a design decision, okay? And so those types of things should be up front from a thought process, because otherwise, hey, we're in a rush, we're being pressured, we need to get it done, we're getting the code, hey, it works, we got to go on to the next thing, and now we don't have sufficient observability about how our software is running in production. So that's a big one. But there's so much here that if anyone's interested in how a .NET application is put together, it's kind of outside of the topic of how you put together the ecosystem in Azure. And I know I talked about the big picture, but this is really for for things for leaders to think about to make sure that your team is properly equipped. I'll end with an analogy, a story actually. Say it again, please. Yeah, I'll show you that. So the key, the question is, when do we create our deployable artifacts? When do we package those up? So the key principle is, if you have one Git repository, you have one application, you have one buildable application. And in the .NET world, it's the Visual Studio solution. You have one per Git repository. You have one continuous integration build per Git repository. Then, because you have one continuous integration build, regardless of branch, you have one method of packaging. And regardless of how many environments we have in our pipeline, you only compile, you only build, compile once. You package it up, whether it's zip file, NuGet package, whatever package format, and you build, compile once, and you deploy many. Okay? That way, when we deploy to production, we know what version that we're deploying, and we know that that exact version has been run through the ringer along the way. Now, I'll show you concretely where we package it up. So you see NuGet push on the screen, which is the task that actually pushes it to the NuGet server, which is in the Azure Artifacts service. And, pardon? Clone it from Git? Oh, cloning is done up here where we specify the source. Is it going to be GitHub, Azure Repos, Subversion, Bitbucket, any other Git repository? And then we give it the URL. So we have given it the URL here. I've authorized this to my GitHub organization. That's where we clone. Then we build. Then we push to Azure Artifacts, which is the built-in package management for deployable artifacts. And right here, I can click on, let's say I can click on the UI, and I can go to versions, and I can see every other version of this package that's here, and it's archived for me. You know what I'm saying? Like, yep. You're continuously deploying, right? So that you've got a developer kind of a continuously changing for every commit to Git, right? Development environment? Right. Does it build? I mean, the answer is no. No, it doesn't build again. It only builds once. So here is the flow. Here is the flow. We have the versioned deployable package. We have the website packaged up in a NuGet package. We have the database migration scripts packaged up in another NuGet package. And we have a full system acceptance test suite packaged up in another NuGet package, because those things have to be deployed to be valuable. And so on the screen here, we have, there's three unique types of environments in a deployment pipeline. We all know production. And then pulling back from production is a manual test environment. And we can call it UAT, call it staging, call it test, whatever. But we have to deploy it to the environment so somebody can check out something and give it a thumbs up or a thumbs down for that particular version. The third type of the unique type is, I call the TDD environment. It's no humans allowed. After the continuous integration build runs, we automatically kick off a deployment to that environment where no humans are allowed, and we see if this thing will deploy. If it will deploy, then we make a web request into the application to start it up, and then we call the built-in system health check. And that can be nothing more than a controller or a web service API that we call from a script calling a URL, a curl line or an invoke web request PowerShell. And then there's a little bit of code inside the application that tickles every one of its dependencies. So for instance, it maybe does a very simple select statement against this database, because if the connection string was malconfigured or the database didn't spin up, that's going to fail, and then that bubbles up and the web request fails, and then the deployment process fails, and we know that that deployment was a failure, because there's no reason for us to let a person go to the website and then have it blow up on them. We can do that automatically after the deployment. The deployment's not successful unless all of the elements of the application spin up appropriately. And so if you integrate with PayPal, if you integrate with the database, with a file system, just write some lines of code that just simply call out and ping those key dependencies so that when you call that built-in system health check, it's giving you a very rich answer that not only am I up and running from a web server perspective, but everything that I depend on is also callable and ready for use. And that way you have a URL that can also then be hooked up to IT monitoring tools and constantly get a rich answer of, am I online? Am I functioning properly? Okay? So that's the progression. And yeah, we only compile once.
Right. But do you, like, as a trigger, like when code is checked in, say, to a development branch, that trigger, or is there
Yep, it triggers. Here's the process we typically use. And by the way, if you like, actually I showed this poster at the 12 Clouds of Christmas, but if you would like a copy, just reach out to me. We have the private build, the CI build, release candidates packaged up, and then full system test. Every single branch goes through that process. Feature branches, everything gets built and deployed to that TD environment. No humans allowed, remember. So we can package up and deploy something from a feature branch. We're not taking up anybody's time. We need to deploy it. Then it's deployed, and we can also run full system tests, and then we can do our pull request because we have confidence that it's ready to be merged into master. Then we can go to our inspection process, and then once it's merged into master, well, now it kicks off another continuous integration build because now there's a commit. And we do the continuous integration build from master, and then we deploy the no humans allowed TDD environment. But then we continue on and deploy to manual test environments. And it's your choice whether you want it automatically fired or somebody has to press a button. You know, you configure it like that. And then, of course, the only builds that can get to production are builds that originated from master or that originated from a production hotfix branch. That's how we typically configure it. All right, let me close with my story. I'm happy to stay as long as you guys would like. My story is this. There we go. There was someone who wanted to open an auto mechanic shop, and he thought to himself, okay, I'm going to get the best of everything. He built a beautiful mechanic shop at a good intersection, and he went to the local auto mechanic school, and he said to the dean of the school, I want your top 7% of the next graduating class. Only the best will do. I'm willing to pay whatever it is. I want the top of your class. And then he goes and he buys brand new crates of Snap-on tools and equipment. Only the best will do. I want to knock this out of the park. Well, this class graduated. They all gathered around the front. They're looking at all this brand new equipment and shiny new tools, beautiful building. And the owner said, all right, team, we're going to open up soon. This will be exciting. Get ready. And he walks away. And all the graduates, top 7% of their class, look around, wide-eyed at each other, because nowhere in the curriculum were they taught how to set up their own environment. And for those of you that have been in the industry for a long time, you know that I was never formally taught how to set up our own environment so the team can be really effective. But we've learned it through just experience and making the mistakes. But as a leader of a team, you have the opportunity to make a big difference by thinking about these things strategically and getting them in place, and watch your team become rock stars. So thank you for being with me. I'll be here for any questions. And back to you, Jeff.